Today you are doing a flame test lab, and first we need to do some notes on page 46. So turn to page 46 and let's do this. In this upcoming flame test lab, you will observe some colors produced when compounds are introduced to a flame. Today we're going to focus on the chemistry of that amazing phenomenon. So what it comes down to is when a compound or an element, an atom in general, is in what's called the ground state versus the excited state. The ground state is when electrons within an atom, electrons in their cloud, are in the lowest energy state. So everything looks normal. Like lithium is 1s2, 2s1, and we could draw that. 1s2 means there are 2 electrons in the 1s orbital. 2s1 means there is 1 electron in the 2s orbital. And if we checked lithium on the periodic table, we could see that here's lithium. That's normal for lithium because we always start at the beginning. Hydrogen is 1s. There's 2 electrons there for those 2 elements. And then when we come down to the next section, lithium is in the 2s, and it is only 1 electron there. So this is normal for lithium. But if you add energy to the atom, an electron can jump up into a higher energy orbital. So what happens, for instance, is that this electron right here might end up moving so that instead of 1s2, 2s1, you have 1s1, 2s1, 2p1, where your 1s still has 1 electron, your 2s still has 1 electron, but then that other electron moved itself up to a higher energy state in the 2p. So what we see are 2 things here. 1 electron is higher energy than it's supposed to be. And the other thing we see is that 1 or more orbitals, 1 or more, I should say, lower energy orbitals, have empty spots they should not have. Because remember, according to the Aufbau principle, the filling up principle, electrons start at the bottom, the lowest energy, and they work their way up. But so you shouldn't have anything in a higher energy level unless everything below it was full. So when you excite an atom and these electrons gain energy, they end up violating the Aufbau principle by moving. One of them will move, and now these lower energy ones aren't full, when if you're going to have something in a higher energy level, they should be full. So we can also mark this. 1 electron is higher energy than it should be. That's that one I highlighted yellow. And then there's also these empty spaces here and here that should not be empty. And we can even see that reflected in the way that the electron configuration was written, that you have this 1 electron that's higher energy than it should be, and then these lower energy orbitals have empty spots they should not have. I'm color coding. I'm sure you can recognize that. So let's practice recognizing before we do anything else. If an atom is in the ground state or excited state, basically to recognize the excited state, something's going to look wrong. So for instance, if we look at this first one, 1s2, 2s1, 2p3, there's a couple different ways you can do this. One way would be you could add up all these electrons. 2 plus 1 is 3, plus 3 is 6. You could go to your periodic table and look for the element with 6 electrons, that's carbon. And you could be like, okay, well, carbon is in the 2p section, but it should only be 2p2. And this would have carbon at 2p3. So this must be excited state. That is a way to answer this question. It's not really the fastest way, but it is a way. A faster way would be to recognize that this 2s1 shouldn't be a 1 if there's going to be stuff in the 2p. Because usually if you have stuff in the 2p, your 2s should be full, and it should be 2s2. So that means that one of these electrons in the 2p has moved up to a higher energy level and left an empty spot down in the 2s. Just like in our lithium example, there was an electron here that moved up to a higher energy level and left these empty spots behind. So that's probably the fastest way to recognize that this is the excited state. If we look at part B, 1s2, 2s2, 2p6, looking at this, we know that all s's have one orbital and can hold 2 electrons at the most. So 1s2, that's full. 2s2 is also full. And then they go on to 2p from there. If all your lower ones are full, then this must be the ground state. That's normal for all the lower ones to be full. And a way you could double check that again is you could add up all these electrons. 2 plus 2 is 4, plus 6 is 10. Go check element number 10, neon. It is in the 2p section, and it is number 1, 2, 3, 4, 5, 6. So this is correct for neon. This must be the ground state. Let's look at part C, 1s1, 2s2. Again, if we think about whether or not these orbitals are full, the s is always, we have one blank, but they've only got one electron in there, and then they move on to 2s. So there is an empty spot here that shouldn't be empty if you're moving on, which tells me this is excited state. And one of these electrons is too high energy. It shouldn't be there. It should be lower down. Plus, again, if you add up these electrons, 1 plus 2 is 3. Element number 3 is lithium. And lithium's supposed to look like this. We already even talked about lithium. And this last one, part D, 1s2, 2s2, 2p3. Again, s's always have one orbital. These are both full. And then they move on to 2p from there. So if all the lower ones are full, that tells you that's normal, and this should be the ground state. There's a table for you to complete below here to do some more practice. Both in this table and down here, I'm going to do 2 of the practices in this table with you, and then you're going to try the other 2 yourself. So first, we have to figure out what element these are asking about. And again, there are multiple ways to do it, but the safest way is to add up all your electrons. 2 plus 2 is 4, plus 5 is 9 electrons total. If you go look at your periodic table, 9 electrons would be fluorine. Or, we could do the next one. 2 plus 2 is 4, plus 6 is 10, plus 1 is 11, plus 5 is 16 electrons. And if you go look at your periodic table, 16 electrons, element number 16 is sulfur. Now, to determine if they're ground state or excited state, again, there's multiple ways you could do this. You could, since you were looking at your periodic table for fluorine anyway, you could check, is it supposed to be 1s2, 2s2, 2p5, basically, is fluorine in the 2p section, and number 5, 1, 2, 3, 4, 5, which yes, it is. Or you could look at, are any of these lower energy levels partially empty? In both cases, 1s2, 2s2, those are both full. On the periodic table, fluorine is supposed to be 2p5. Both of those things are clues that this fluorine's in the ground state. But when we go look at the sulfur example, again, two ways to do it. If you're looking at your periodic table anyway, you may check, is sulfur 3p5? Sulfur is in the 3p section, but it's supposed to be number 1, 2, 3, 4. Which tells me that somewhere there's an extra energy electron. One of these fifth ones, one of these 5 in the 3p5, has more energy than it should. And if we go back and look through, is there an orbital section that's not full? Well, 1s2, 2s2, 2p6, 3s1. Oh, there it is. That's one that's not full. That tells me this is excited state. And I want to do one of the ones in number 3 with you. Are these orbital notations stable, excited, or just wrong? Well, in part A, we've got 1s2, 2s2, 2p2, but, so we've got all the lower energy levels are full, so that tells me it's not excited. Deciding if it's stable, meaning like normal, correct, versus if it's just wrong, you should notice something about these electrons here. Like in the 1s, they're both up, and the 2s, they're both down. Remember, to be correct, you should always have one up and one down. One up and one down. And then in the 2p, if we're following Hund's rule, or the good mother rule, then you shouldn't have any that are sharing an orbital if there are empty orbitals. So your 2p, to be correct, should look like this instead. Which tells me that this one, part A, is just wrong. Okay, you can pause the video real quick and finish this chart and answer part B. Then I'll go over them super fast, and then we'll move on. So pause the video. And if you're playing the video at this time, let's look back at this chart real fast. 1s2, 2s2, 2p5, 3s2. If you add up all of those electrons, there are 11, and that tells you this is supposed to be sodium. If you're checking for ground or excited state, this 3p5 here, or excuse me, 2p5 here, should be a 2p6 if you're going to be moving on to 3s2. That tells me there's an empty spot that shouldn't be empty, and one of these 3s2 electrons is too high energy. This is excited state. And if we look at this one right here, 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 3 is 15. And 15 electrons is phosphorus. And again, you could look at the periodic table and check, is phosphorus supposed to be 3p3? It is. You could also notice all of these lower energy ones are full. Both of those are clues to tell you this is ground state. If we look at part B, we've got 1s looks correct. There's an up and a down. 2s, you have just an up. 2p, you have 3 ups, each in their own orbital. There's nothing really wrong with this. What we really have is we have an empty spot that shouldn't be empty, which means that one of these electrons is just higher energy than it's supposed to be. So this is excited. And when you're done writing that, you can turn the page. So thinking about the structure of an atom, we can continue forward with this example of ground versus excited state and how this works. So in the ground state, electrons are found at their lowest energy level, which for lithium, remember, lithium was 1s2, 2s1 in its ground state. We just looked at that on the previous page. So we can draw those electrons in. Here's the 1s2. Then 2s1, that means we move out to the second shell and we put one electron in there. But if you add energy, an electron can get excited. When you add energy in the form of fire, like heat, or high energy light, like UV light or black lights, electrons can jump up to a higher energy level. So what ends up happening is that, like maybe this electron that was in a lower energy ground state might end up jumping out further away from the nucleus. You can't really see that. And so it ends up where you have two electrons that are where they started, and then you have another electron that has jumped out. And you know what, just to make this more dramatic, we'll have it jump all the way out to the third shell, because that's totally possible. So maybe it's jumped all the way here. It's got too high of energy, and you've got empty spots that aren't supposed to be empty. There's this empty spot here, and then there's a bunch of empty spots in the second shell. Both the 2s and the 2p are empty, and I've had this guy jump out to like 3s1. So we have all this empty lower energy levels with empty orbitals. But then, when it returns to the ground state, the electron can fall back down to its lower energy level, so that basically you've got these two that stayed low the whole time, and then that guy that had moved goes back to where he was. And when that happens, energy is released, sometimes in the form of light. So he started out here with too much energy, and he jumped back down to where he started, so he's not here anymore. But when he did that, when that electron did that, it released energy in the form of light. And what you're going to find in the lab is that you can get all kinds of different colors of light coming from this, and that's going to depend on how far the electron fell. So we're going to write that down too. Different colors of light depending on how far the electron falls. And when you're done writing that, you can turn the page. So, why are the different energies of light different colors? You have to remember when we were talking about the electromagnetic spectrum and waves, it turns out that different energies of light have different wavelengths, and the way that human evolution has worked is that our eyes perceive different wavelengths of light to be different colors. So red light has longer wavelengths than like violet light. Those are very short wavelengths. And our eyes perceive these different wavelength ranges as different colors. So there is a range in which we see light as red, and then we hit the edge of that range and it starts looking more orange to us, and that's based on how long those wavelengths are. So first, what we're going to do here is convert these wavelengths from nanometers to meters, and to do that you divide by 1 times 10 to the 9th, so 1e9 in your calculator. And when you do that, you're going to start seeing a pattern. So in your calculator, type 750 divided by 1e9. And you get 7.5 times 10 to the negative 7. That's your first part of your range. And then it goes to 620 divided by 1e9. You get 6.2 times 10 to the negative 7. Please make sure that when you type it in your calculator, it looks like this. If it doesn't look like this, you are typing something wrong. I will point out that when you get down to orange, you're doing 620 again, so this divided by 1e9 is still going to be 6.2 times 10 to the negative 7 for your first part of your range, and then this comes out to 5.9 times 10 to the negative 7, so on. I'll let you finish this yourself, and Miss Woodlock can check it for you. But I do want to make sure that we discuss like how this is useful. So what we're going to do is see some examples down here of different colors, and we have to determine like what wavelengths of light we're likely to see with those. So I'm going to do 2 of them off this chart with you. I'm going to talk about orange yellow, and I'm going to talk about bright red with you. And then you're going to determine the other 2 yourselves after you finish this chart at the top. So if you see orange yellow light during the lab, and you need a wavelength for what that light would be, well, if we go back to this chart, there's an orange range, and there's a yellow range, and there's a spot where they overlap at this 5.9 times 10 to the negative 7. So we can estimate that the wavelength of the light you saw was about 5.9 times 10 to the negative 7 meters, or 590 nanometers. And I'm literally just taking that from the chart and looking at where this range overlaps. Okay, another one, bright red. Red has this range from 750 to 620. If I pick the 620 side of the range, that's overlapping with orange. And I don't want red-orange. This example wants just bright red. So I should probably pick the 750 side of the spectrum. Or 7.5 times 10 to the negative 7 meters. Okay, so that's how this is going to work when you get to your lab. And from here, I'm going to let Miss Woodlock explain the lab itself. But let's go to your stamp page real fast. Okay, at this point in time, I am pretty sure that we should be looking at, it's probably either the 18th or 19th, but it might be the 20th or 23rd, again, depending A day or B day. So here are your options, and obviously whichever one it actually is the one you should write down. This is for a lab grade, And the actual pages you're doing are page 48. And then, let's see, it kind of skips a couple. 48, I think it's 51 and 52. Yes. Page 48, 51, and 52. So it skips a couple pages in there. Okay. So that's going to be your stamp. It is for a lab grade. So the stamp today is just checking that you participate, and then there will be a full grade on like the correctness of the lab in the lab section of the grade book. And I'll hand it over to Miss Woodlock.